Assalamualaikum. Welcome back to Sir K Lab's Physics and Chemistry tutorial for high school students. This episode is a continuation of the lessons on gas laws. This time, we solve problems involving Graham's law of effusion. Please stick around till the end of the video. Watch and learn. The questions are: number one, at a particular pressure and temperature, nitrogen gas effuses at the rate of 79 milliliters per second. Under the same conditions, at what rate will sulfur dioxide effuse? Question number 2. Hydrogen gas effuses through a porous container 8.97 times faster than an unknown gas. Estimate the molar mass of the unknown gas. Question number 3. A party balloon filled with helium deflates to two-thirds of its original volume in 8.0 hours. How long will it take an identical balloon filled with the same number of moles of air whose molar mass equals 28.2 grams per mole to deflate to one-half of its original volume? Graham's law of effusion states that the rate of effusion of a gas is inversely proportional to the square root of the mass of its particles. The ratio of the rate of effusion of gas A to that of gas B is equal to the ratio of the square root of the molar mass of gas B over the square root of the molar mass of gas A. What's the difference between diffusion and effusion? When the gas molecules spread out without any restriction, that is called diffusion. When the gas molecules are restricted to pass through very small openings in a physical barrier, then that process is called effusion. In these figures, two balloons are inflated with different gases. The orange balloon contains helium gas, while the blue balloon has argon gas. After 12 hours, we see the orange balloon more deflated than the blue balloon. This is because of the greater rate of effusion of the lighter helium gas. Answering the given questions now, for question number 1, we are given the rate of effusion of nitrogen gas equal to 79 milliliters per second. and its molar mass of 28 grams per mole. You're also given the molar mass of sulfur dioxide gas equal to 64 grams per mole, and we are asked to determine the rate of effusion of sulfur dioxide gas. So, using the equation of Graham's law of effusion, we isolate our target variable, all right, that is, the rate of effusion of sulfur dioxide is determined by multiplying the square root of the molar mass of nitrogen gas times the rate of effusion of nitrogen gas. So their product will be divided by the square root of the molar mass of sulfur dioxide. So when we substitute, all right, the rate of effusion of sulfur dioxide gas will just be equal to square root of 28 times 79 milliliters per second to be divided by the square root of 64. And doing our math, we arrive at the value of the rate of effusion of sulfur dioxide equal to 52 milliliters per second. To two significant figures. And as expected, this is lower than the rate of effusion of the lighter nitrogen gas. In question number 2, we are told that the rate of effusion of hydrogen gas is 8.97 times the rate of effusion of an unknown gas, which we label as gas X. The molar mass of the hydrogen gas is of course equal to 2.0 grams per mole. And the target variable here is the molar mass of the unknown gas X. Again, based on Graham's law of effusion equation, the ratio of the rate of effusion of the unknown gas to that of hydrogen gas is, all right, 1:8.97. So, we equate this ratio, all right, to the square root of 2.0 grams per mole, right? And divide it by the square root of the molar mass of the unknown gas. And solving for the molar mass of the unknown gas, all right, we get the square of 8.97 to be multiplied by 2.0 grams per mole. So, we get as our answer the molar mass of the unknown gas equal to 161 grams per mole. All right. Again, as expected, this is a lot greater compared to the molar mass of the hydrogen gas. For our last question, question number 3, we are told that the helium-filled balloon deflates 2/3 of its original volume in a time of 8.0 hours. And we are asked to find the time it takes for an identical balloon filled with the same number of moles of air to deflate to 1/2 of its original volume. So, we can express the rate of effusion of helium gas as 2/3 of its initial volume, capital B, divided by 8.0 hours. And we'll be using the molar mass of helium gas equal to 4.0 grams per mole. The rate of effusion of air can also be expressed as 1/2 times the initial volume, capital B, alright, divided by the unknown time of small letter t, right? With the molar mass of the air given as 28.2 grams per mole. So, we can simplify the rate of effusion of helium gas, right? Since the initial volume, capital B, is the same for both gases, we can just cancel it. And the rate of effusion of helium gas, therefore, is just equal to 0.083 per hour. And similarly, the rate of effusion of air is also simplified, all right, as 0.5 per the unknown time small letter t. And as usual, we will be using the Graham's law of effusion equation. That is, the ratio of the rate of effusion of air to that of helium is just equal to the square root of the molar mass of helium divided by the square root of the molar mass of air. Substituting the quantities to our equation, we have 0.5 per the unknown variable small letter t over 0.083 per hour, that is equated to the square root of the molar mass, 4.0 grams per mole, or that's simply equal to 2. And that will be divided by the square root of 28.2 grams per mole, or simply 5.3. So cross multiplying, we get 5.3 times 0.5 over the time t will give us 2.7 divided by the small letter t, all right, being equal to the product of 0.083 per hour, okay, and 2.0, which is equal to 0.17 per hour. And solving for the time t, this is the time for air, all right, that will just be equal to 2.7 divided by 0.17 per hour, or the time t is equal to 16 hours in two significant figures, right? So this means that it takes 16 hours for the air-filled balloon to deflate to 1/2 of its original volume, right? We can actually check our answer, right, by computing the ratio of the rate of effusion of the helium gas to that of air. So for helium or helium gas, we have 2/3 multiplied by an assumed volume or initial volume of 1.0 liter for simplicity, and then divided by the given time, which is 8.0 hours. All right, simplifying, that gives us 0.083 liters per hour. So likewise for the air-filled balloon, all right, so the rate of effusion for air is 1/2 multiplied by the same assumed volume, 1.0 liter. And that will be divided by the computed time of 16 hours. So we will get the rate of effusion for the air equals 0.031 liter per hour. Okay, so that gives us the ratio for the rate of effusion of helium to that of air equal to, by dividing 0.083 liters per hour by 0.031 liters per hour, that gives us the ratio 2.7. Alright? Likewise, we also get the ratio of the molar mass. Alright? Or the ratio of the square root of the molar mass of air to that of helium. That is square root of 28.2, okay, grams per mole divided by the square root of 4.0 grams per mole. Right? So doing our math, we will get actually the same value for the ratio, equal to 2.7. All right? So our computation for the two ratios, okay, agrees with our Graham's law of effusion. And that concludes our tutorial for this topic. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.